Hello, my name is Dan Dan. Today I'd like to talk about the operation of a three-phase motor. As you can see here on the left-hand side, he's my older boy called Jethro, and on the right-hand side, he's my younger boy called William. They're 12 and 8 years old. So I'd like to begin with electric vehicles. So electric vehicles are becoming very popular these days. There are several reasons for a lot of people are continuing showing interest in these vehicles. Because they create less pollution than gasoline-powered or petrol cars. So they're environmental friendly, especially in cities. An electric car is a car powered by an electric motor rather than a petrol engine. So from the outside looking, you will probably have no idea the car is powered by an electric motor. Here I'd like to talk to you about electric vehicles, we also called EVs, and the gasoline cars. What are the difference? So for the EVs, they are more environmental friendly, less pollution than gasoline or petrol cars. Electric cars are powered by electric motors rather than petrol or diesel engines. So when you drive an electrical car, the only thing that strikes you with its true nature is that it's almost silent. It gets energy stored in its rechargeable battery, which can be recharged by common household electricity. Electric cars use battery charger and gasoline cars use gas tank. Electric cars has motor and gasoline cars has engine. Electric cars has no bagpipes, no pollution. So some of you might ask, what are the difference between engine and motor? Do you know the difference? So the major difference for an engine, it converts thermal energy into mechanical energy. And for a motor, it converts any energy into mechanical energy. Could be electrical energy or gasoline, diesel, petrol energy. Therefore, an engine is a type of motor, but a motor is not necessarily an engine. An electric motor from an EV converts electrical energy to mechanical energy. So how does an electrical vehicle work? Electric vehicles are like an automatic car. They have a forward and reverse mode. When you place the switch in gear, if you press the accelerator pedal, power is converted from the DC battery to AC for the electric motor. The accelerator pedal sends a signal to the controller, which adjusts the vehicle speed by changing the frequency of the AC power from the inverter to the motor. The motor connects and turns the wheels. When the brake pedal is pressed, the motor becomes a generator and produces power which sends it back to the battery. Here are the major EV parts. As you can see on the top left, second left, that's the batteries instead of gas tank. On the top right, it has electric motor instead of engine. On the back of the car has no tailpipe. It has power inverter. On the top right, it has power electronics controller. On the middle top, it has charge point. Bottom left, it has DC-DC converter. Bottom right, and transmissions. So if you want to understand how an electric vehicle works, you need to be familiar with the physical elements of an electric motor. The most common type is three-phase induction motor, and start to understand its two major parts, the stator and the rotor. When connected to electrical power, the stator, which is stationary, generates a rotating electromagnetic field. It uses electrical energy to create a magnetic field and hence turns the rotor. Connects to the shaft is the rotor, which is rotating. In this case, is a squirrel cage type rotor, because it has two end rings connected with its bars, and these are all rotating together. This type is similar to a pet hamster or a squirrel cage. The squirrel cage is fitted with a number of laminated steel sheets. The sheets will help to concentrate the magnetic field into the bars. This is to increase the efficiency as well as to reduce the eddy current. The rotor is placed in the stator. As the power is connected to the stator, the rotor will start to rotate. So how does this work? When electricity passes through a wire, an electromagnetic field is generated around the wire. We can use the right-hand rule to find the direction of the current flowing, induced by the magnetic field. Now if we wrap the wire into a coil, the magnetic field will be stronger. The coil will produce a south and north pole just like a permanent magnet, as you can see on the right-hand side of the third diagram. We call these coils of wire an inductor. When we pass an alternating current through the wire, the electrons will constantly change direction between flying forward and backward. So the magnetic field also changes constantly, so the polarity changes each time. Now if we place a wire in a magnetic field and pass the current through it, the magnetic field of the wire will interact with the magnetic field of the permanent magnet, and the wire will therefore to experience a force. This force will move the wire either upwards or downwards, depending on the current and the polarity of the magnetic field. Now when we place the separate coil close to the existing coil and complete the circuit with a bulb, the electromagnetic field will induce a current in the second coil. We can connect two coils together to create a larger magnetic field. If we place a closed loop of wire inside the magnetic field, we will induce a current in the loop. So this loop of wire will also generate a magnetic field, and this field will interact with the larger magnetic field. Each side of a coil will experience a force which causes to rotate. This loop in the middle of the picture is called a rotor, and the coils are therefore a stator. The rotor will only rotate until it aligns with the stator coils. At this point, it will likely to get stuck. To overcome this, we need to introduce another set of coils in the stator. We must connect these to another phase. The electrons that are flowing in these coils are in slightly different time. So the electromagnetic field will also change strength and polarity in different time. This will force the rotor to rotate. In an induction motor, we have 3 separate coils, which are used to produce a rotating electromagnetic field. When we pass an alternating current to the coils will produce an electromagnetic field, which changes intensity as well as polarity as the electrons change direction. But if we were to connect each coil to a different phase, then the electrons in each coil will change directions at different times. This means the intensity and polarity of the magnetic field will also occur at a different time. To distribute this magnetic field, we need to rotate the coils at 120 degrees from the previous phase. We then combine this into the stator. This combined to produce a rotating magnetic field in the stator. The bars of a squirrel cage rotor are shortened at each end, as you can see on the picture, therefore created a multiple loops of coils. Each bar therefore induces a current and creates a magnetic field. The magnetic field of the rotor bars interacts with the magnetic field with the stator. As the stator magnetic field is rotating, the rotor is therefore also rotating at the same direction of the stator magnetic field to try and align with it, but it will never fully catch up. Okay, so that's it for today's operation of a 3-phase motor. Sorry, it went over just 2 minutes. Thank you very much for listening. Any questions, please feel free to email or call me anytime. I look forward to seeing you all very much tomorrow. Have a good afternoon. Bye for now.